Hi, welcome to number 9, looking at analog inputs, and we're just going to dive straight in. First, some important items. I'd like you to subscribe to the channel. I need all the help I can get. Click on the like button because obviously you're going to like this video. Then click on the bell notification icon to get notified of all updates. And finally, support me on Patreon if you can, please. There's a link in the description below. All donations gratefully received. Here's the code we're going to use today in the live lab. The global event handlers down the bottom. We've got some variables up the top that I'd like to talk about because we're going to be using lots of different ways of looking at analog handling. So first of all, pole frequency. A lot of these analog values are done on a polling basis because they're generally values that you don't need to check 100 times a second. So we've got a nominal figure in there of every 5 seconds just to demonstrate some features. We've got another thing here which we're calling N samples, which we'll come to, but hysteresis is something we need to talk about. It's an interesting word. If you know what it means already, that's fine, but in this context it means the amount by which the analog value needs to have changed before you consider that it's a new value. So some people might call it wiggle room, some people might call it a dead zone, but for a value of 10 as we've got here, look, what that means is if you read the ADC and the raw value is 226, and the next time you read it it's 235, that's only 9 away. So it treats it as if it hasn't changed. It would have to be at least 246 or whatever it was, 10 plus. And that is a useful way of reducing the amount of flipping and flopping backwards and forwards that some sensors can do. So moving rapidly on, let's look what the complex hardware we've got in the live lab today. It's a piece of wire stuck into the analog input. I don't have many sensors that would be any use for this. I don't do a lot of analog type of work, but what I do know is that it's real easy to wet your fingers and use your galvanic skin response to actually get a value on that ADC. So there we go, look, we've got a value of 49. And this is the important point about the pole. It doesn't do it every 5 seconds. What it does is check every 5 seconds if the value has changed. And it checks if the value has changed by more than the hysteresis. So let's just pause that. A couple of things have changed. I've changed the frequency down to 1000 to make life a little easier. I've recompiled it so that we're now using this analog average, and the way that the analog average works is this: every 1000 milliseconds now it takes 5 samples, so each of those samples will be 1 second apart, 1000 milliseconds a second. So that is going to give me a value of the average every 5 seconds. Now then, because I'm taking that average, it doesn't do this thing where it will only do it if it's changed. So it will take 5 readings and average them out. So if I take this out and now ground it so that the instantaneous value is 0, you can see that the average 5 seconds later has gone down, and 5 seconds later it's gone down again to 0. you'll also see that it's still being reported every 5 seconds. Okay. So because it doesn't want to stop doing the readings between each successive reading, it just doesn't stop at all. It just takes 5 readings once a second in a loop and spits out the average of them. So it's quite a dumb way, but just watch that happening again. I will now put my wet fingers on it to give it some kind of middling type of value. 5 seconds. No, it's not liking that, is it? Let's stick that in the high. There we go, and then gradually it will increase, because even though the instantaneous value is 1023, the value over 5 averaged out isn't quite that amount. Let us move on. This time we are looking at an analog average changed. Oops, I'm actually holding that at the moment, giving it some values so that it will change. So this is very much like the previous one, but it will only send the value when it's changed. Because we're dealing with a changing value, we have the hysteresis in there. So this will take 5 samples, or however many you decide, over a period of 1 second per sample. It will then take the average of them, and if that's different by more than the hysteresis from what the last time it said, it will then spit out the value. And obviously my grip on that wire has become so weak that the power has gone down to 0. And you can see there that if you leave it floating, you still get readings off it. So if that settles to the point where it's genuinely getting a 0, that you won't see another value come out of that at all until it changes again. So I've got to wait at least 5 seconds to prove the point. I think that's probably enough. As soon as I change the average value over the next 5 seconds by holding onto that wire, hopefully that's got at least a couple of readings in it now, enough to change it. Yep, there we go. So there was a residual value there. Okay, let's move on to the next one. What we have now is an H4P analog average window. So that's using the same 1 second pole frequency, and it's using the same 5 samples. But what we have here is what's called a sliding window. So instead of going 1, 2, 3, 4, 5, take the average, 1, 2, 3, 4, 5, take the average, every second it takes the average of the last 5. And then the next second it'll drop one off the back, pick a new one up off the front, so it's always calculating the last 5 sliding window. So as you can see from the live cam, it's just floating at the moment. It happens to be picking up a floating value of 1. So what I'm going to do is the old lie detector test again. There we are, look, we've got a small value, and you can see that gradually that's increasing, stabilizing out around about 200 whatever. If I let go, obviously the reading is going to drop away and decay away. Eventually it'll get back down to 0, but again this is another one that just keeps on sending all the time. So if we stick it in the positive rail, gradually climb all the way to the maximum and continue to throw out the maximum. As we put it to ground, it will decay down to 0 and continue to spit out 0. Sliding window. Right, what's next? What's next is the analog average rolling, and this produces a cumulative rolling average, as mathematicians would call it. I'm going to start that compiling. I'll just pause until that's finished. Right, that's finished cooking and it's off and running once per second, as you can see. Now, I'm not going to go into the maths in detail. You can Google for what a rolling average is. But this is going to change a lot more slowly than the last one, which is a sliding window of 5, because this takes into account every value it's ever been. So it's an average of how it has changed over time, if you like. So by definition, it's going to change slowly. So what I'm going to do is just pop that into the maximum, and we'll see how long it takes for that to rise up, because when it takes the average now, it's got to take the average of all those dozens of low values that I put into it to start with. So it is going to take a while to climb, and once it's got to a sensible high value, gradually the amount by which it's going up will increase all the time. It's kind of accelerating upwards. What's it adding each time now? 9. Oh no, oh, gradually, no. And as it reaches the maximum, it'll slow down the amount which it reaches it. But that's, you know, do we need to wait any longer? You get the idea. Let me ground it now. And you'll see it going back down again. There we go. So the rolling average is going down, but a lot more slowly because of the way we're calculating it. Let's cook up the next one to see what that does. This next one's slightly interesting. I don't have many analog sensors, but one of the few things I do use is a thing called a TMP 36. Lord knows why I've called it a 236 there, but it's a little temperature sensor. I haven't got one at the moment. I'm not going to bother hooking one up. You just have to take my word for it that if I had one connected to the yellow wire, it would read me out the current temperature based on a little calculation that I do. So obviously the value you're going to see is going to be bizarre and wrong, because I'm going to be using my wet fingers to simulate it. But again, we have some hysteresis. Let's just run it up the flagpole and see who salutes it again. Stand by. So here we are looking at a simulated TMP36. You might be able to see from on the live cam that basically I've just stuck it in the positive rail, which means that the figures that I'm getting off it are just nuts, because that's telling me it's 266.9 degrees, etc., etc. Also, what you can see is the amazing fluctuation in the values, and that's another reason why I don't use analogues very much on an ESP8266 anyway, because it's absolutely rubbish at reading an accurate value when using Wi-Fi. But you're not using Wi-Fi. Yeah, I kind of am in the background. You're not seeing it at the moment, but that's a different story. The point is, I don't get very good results from anything analog off of this off the ESP devices. But let's stick that back down to 0 just to see it changing. And that temperature is now minus 50, and I'm in theory should be freezing to death. But let's just put some intermediate values on it, just to show you that in the meanwhile it should, it should give sensible values-ish. I find it's generally 3, 4, 5 degrees centigrade out from the actual value, but this doesn't seem to like changing particularly easily at the moment. No, let's give it a known value. Start. There we go. Yeah, crazy wild. But you get the picture. There we are, look, 5.9 degrees Celsius, 1.8 degrees, minus 2.1, minus 14.2. And all of this, look, yes, you're going to get a degree of fluctuation because it's a loose wire and because it's got human fingers which are infallible, but look at the crazy readings you get off it. Right, there we go. We have one more to look at, and it's called an analog threshold, and it's a way of making a very expensive ADC into a very cheap digital I/O pin. So let me just start that We'll just start that compiling. I can always pause this later if I run out of things to say before it's ready to test. So what we have here is this. We're going to take a reading and we're going to compare that reading with a value. And if the reading is greater than, oh, there we go. Oh, there's a bug I've got to fix. I should have spotted that. I'll fix that and get back to you in a second and carry on explaining. Yeah, apologies for that. Some of the names have changed from the previous version and I forgot to update that one. But what that says is this. If the value is greater than 100, plus or minus the hysteresis, then send a value. If it's not, don't. So basically we've turned an analog pin into a kind of binary pin. If it's either above or below the value that we choose, we get a message, otherwise we don't. And we can choose a method of greater or less, and that's the base value. So that's set to 100. So if it's greater than 100, we should get a signal. So let's just try and put some lie detection on it. No, that's not going to work. Let's whack it in the positive rail. There we go. So when I then take it out and stick it in the negative rail, I'll get nothing, because I only get a message that's greater than the threshold. Okay, I think we're just about done then. I have to wait the 30 seconds to stick that interesting stuff on the end. So thanks for watching. I look forward to doing you in the next video, which won't be on GPIO because we've done all the GPIOs. Oh no, I'm lying, it will be. Never mind.